Welcome to the Deep Dive. We're the podcast that cracks open sources to bring you those really crucial bits of knowledge.
Glad to be here.
Today we're diving into something you probably think you know inside out. The word pure.
Yes, pure. It's everywhere, isn't it? You see pure juice, pure gold.
Pure intentions even.
Exactly. But, what does pure really mean when you look at it through a scientific lens? Because it's often quite different from how we use it day to day.
Totally different. And here's where it gets, well, fascinating. You pick up milk, label pure, right?
Yeah.
You think, okay, it's just milk, nothing added.
Simple enough, you'd think.
But for a scientist, that same carton of milk is actually this amazing complex mixture. It's got water, fats, proteins, lactose, all sorts of things. Scientifically, it's pretty much the opposite of pure.
It really highlights how science needs that precision in language, doesn't it? Precision our everyday chat often just smooths over. Understanding that difference is key.
So that's our mission for this deep dive. We want to unpack what pure genuinely means in science.
Wow.
We'll explore all the different kinds of mixtures around us, and there are loads. And then we'll break down matter into its basic forms. You might find some surprising facts that, well, change how you see the everyday stuff around you.
Definitely. It's fundamental.
Okay, let's jump in. So you mentioned that milk isn't scientifically pure. So what is? What does it take for something to get that label in science?
Right. Well, in science, a pure substance is all about uniformity. It means every single constituent particle is chemically identical, the same.
Just one type of particle, then?
Exactly, just one kind. Think about, say, table salt sodium chloride or pure sugar. It doesn't matter where it comes from, its chemical nature, its properties, they're always the same. Its composition is fixed. That consistency is what makes it scientifically pure.
Okay, that's super clear. One type of particle, fixed properties. So then most things we encounter must not be pure, right? They must be mixtures.
You got it. That takes us into the huge world of mixtures. Mixtures are just, well, made up of more than one kind of pure substance combined together.
And they're everywhere.
Absolutely everywhere. Look around. Seawater. That's water, salts, minerals. Soil is a massive mixture. The air we're breathing right now. A mixture of gases. Even things like metal alloys. All mixtures.
So the key thing with seawater is that the salt is still salt, and the water is still water, even when they're mixed.
That's the crucial point. The components in a mixture mostly keep their own individual properties, and because they're still themselves, chemically speaking, you can often separate them using physical methods.
Ah, okay.
Like you said earlier, you can boil off the water from seawater and you're left with the salt. They didn't chemically change into something new, they were just sharing the same space.
That makes sense. Physical separation works.
Yeah.
Now, our sources mention two main kinds of mixtures, homogeneous and heterogeneous. Can you break those down?
Sure. Let's start with homogeneous mixtures. We often just call these solutions. Homogeneous means they have a completely uniform composition all the way through.
Uniform, meaning it looks and is the same everywhere.
Exactly. Imagine dissolving, say, some blue copper sulfate powder in water. You stir it up, and the whole thing becomes uniformly blue. Every drop has the same color, the same concentration.
Right, like dissolving sugar in tea. Once it's dissolved, every sip tastes the same sweetness. It's all mixed evenly.
Precisely. Even though the amount of sugar might vary from cup to cup, within one cup, it's uniform.
Okay, so that's homogeneous. What about the other type? Heterogeneous.
Heterogeneous mixtures are the opposite. They contain physically distinct parts, and their composition isn't uniform. You can often actually see the different bits.
Oh, like
mixing sand and sugar, you can see the individual grains, or iron filings mixed with sulfur powder. You can spot the shiny metal and the yellow powder. Oil and water is a classic one, too. They just don't mix. They form separate layers.
Yeah, you can definitely tell those aren't evenly mixed just by looking. The different components are clearly visible and separate. Okay, we've got the basics of mixtures down, homogeneous, heterogeneous. Now let's zoom in a bit on solutions, suspensions, and colloids, because this is where it gets really interesting and maybe challenges how we think about mixing.
It really does.
We know solutions are homogeneous, but you mentioned earlier they aren't just solids dissolved in liquids, right?
Oh, absolutely not. That's a really common misconception. We think of salt and water, but solutions can happen in any state of matter.
Like what?
Well, take solid solutions. We usually call these alloys. Think about brass used in musical instruments, fittings. It looks like one uniform metal, right?
Yeah.
But it's actually a homogeneous mixture, typically around 70% copper and 30% zinc dissolved together. Its properties are a blend, and you can even vary the percentages somewhat. It's still a solution.
Wow. Okay. a solid solution. And gases, you mentioned air.
Air is the perfect example of a gaseous solution. It's a homogeneous mix, mostly nitrogen, about 78%, and oxygen, about 21%, plus small amounts of other gases, all dissolved in each other. So yes, solutions are much more diverse than just liquids.
That really broadens the definition.
Yeah.
Now, in any solution, you have the things being mixed. The sources call them the solvent and the solute. How do we know which is which?
It's pretty straightforward usually. The solvent is the substance that does the dissolving. It's typically the component present in the larger amount.
Like the water and salt water.
Exactly. Water is the solvent there. The solute is the substance that gets dissolved, and it's usually present in the smaller quantity. So the salt is the solute.
Okay.
Other examples. Iodine dissolved in alcohol that makes tincture of iodine. Alcohol is the solvent. Iodine is the solute. Or carbon dioxide gas dissolved in water for fizzy drinks. Water is the solvent. CO2 is the solute.
Got it. Solvent does the dissolving, usually more of it. Solute gets dissolved, usually less of it. Simple enough.
Now, besides just being homogeneous, true solutions have some really specific properties that make them unique.
Okay.
We said they're homogeneous. Also, the solute particles are incredibly tiny. We're talking less than a nanometer across. Way too small to see, even with a basic microscope.
Wow, really small.
Yeah, and because they're so tiny, they don't scatter light. If you shine a beam of light through a true solution like sugar water, you won't see the beam's path. It just goes straight through.
Huh. That's interesting. So they look perfectly clear or transparent because the light isn't bouncing off anything?
Pretty much. And finally, they're very stable. The solute particles won't ever settle out no matter how long you leave the solution standing. And you can't separate them using a simple filter like filter paper. The particles are just too small, they go right through.
Okay, stable, tiny particles, don't scatter light, can't be filtered. That's a good set of characteristics. Now, you mentioned earlier that even if a solution is uniform, it doesn't mean it always has the same strength, right? Like my tea example, little sugar or lots of sugar.
Exactly. And that leads us to the idea of concentration. How much solute is actually dissolved in the solvent? Our sources talk about dilute, concentrated, and saturated solutions.
The saturated sounds full.
It is. A saturated solution is one that holds the absolute maximum amount of solute it can possibly dissolve at a particular temperature. If you add any more solute, it just won't dissolve. It'll sit at the bottom.
And the amount it can hold is called its solubility.
Yes, precisely. Solubility is the measure of how much solute dissolved in a saturated solution at a given temperature.
So if you haven't reached that maximum limit yet, it's...
That's an unsaturated solution. It could still dissolve more solute.
Okay. And temperature matters here, you said.
Oh, hugely. Solubility changes with temperature. For most solids dissolved in liquids, heating things up allows you to dissolve more solute. Think about dissolving sugar in hot coffee versus iced coffee.
Right, much easier in hot coffee. You can get way more in before it just sinks to the bottom.
Exactly. And, scientists need ways to be precise about concentration. The source mentions using percentages, like mass by mass percentage.
Yeah, it had that example. 40 grams of salt and 320 grams of water. The total solution is 360 grams. The concentration is 40 divided by 360 times 100, which is about 11.1% salt.
Right. It gives you a specific number much more precise than just saying dilute or concentrated.
Okay, that covers solutions pretty well. What about the next type? Suspensions. How are they different?
Well, suspensions are sort of the opposite of solutions in many ways. First off, they're clearly heterogeneous. The solute particles in a suspension don't actually dissolve. They just hang suspended in the liquid.
Like mud and water.
Ah,
Or flour in water before you mix it properly.
perfect examples. Chalk powder in water is another good one. You can see the individual particles floating around, especially if you stir it up. They're not dissolved.
So visible particles, definitely heterogeneous. What else defines them?
Because the particles are much larger, they do scatter light. You can easily see the path of a light beam going through muddy water. Ah, okay. Unlike solutions.
Right. And crucially, suspensions are unstable. If you let that muddy water sit for a while, what happens?
The mud settles to the bottom.
Exactly. Gravity pulls the particles down. They don't stay suspended forever. And because they settle and the particles are large, you can separate them by filtration. You can filter muddy water and get clearer water out.
Okay, that makes sense. Visible particles, scatter light, unstable, filterable. Quite different from solutions. Which brings us to that intriguing middle ground. Colloidal solutions, or just colloids. The source says they look homogeneous but are actually heterogeneous. That sounds tricky.
They are a bit tricky. Colloids are fascinating because their particles are spread out uniformly, so they often appear perfectly smooth and homogeneous, like milk or mayonnaise.
But they're not truly homogeneous.
No. Technically, they're heterogeneous.
Yeah.
The key is the particle size. It's in this intermediate range, bigger than particles in a true solution, but much smaller than those in a suspension, usually somewhere between, say, 1 and 1,000 nanometers.
And that specific size gives them unique properties. It really does. The most famous is the Tyndall effect. Have you heard of that?
Vaguely. Something about light scattering.
Exactly. Because the colloidal particles are just big enough, they scatter a beam of visible light that passes through them. This makes the actual path of the light beam visible. It's named after John Tyndall, the scientist who studied it.
Oh, right. Like when you see sunbeams streaming through a dusty window.
Mm.
You can see the beam itself because of the dust.
Perfect example. Or sunlight filtering through mist or fog in a forest. The tiny water droplets in the mist are colloidal particles scattering the light. That's the Tyndall effect in action.
That's a cool visual. So properties of colloids, they look uniform but are heterogeneous.
Mhm.
Particles are too small to see individually, but big enough to scatter light via the Tyndall effect. What about stability? Do they settle like suspensions?
No, that's another key difference. Colloids are generally quite stable. The particles don't settle down on their own over time, unlike suspensions. Think about milk. The fat globules don't just sink to the bottom quickly.
Right. And filtration. Can you
Yeah.
filter them?
Nope. Simple filtration doesn't work because the particles are still small enough to pass through filter paper. However, you can separate them using a technique called centrifugation.
Ah, spinning them really fast.
Exactly. A centrifuge spins the colloid at high speed, and the force generated pushes the denser particles outwards, causing separation. That's how cream is separated from milk commercially.
Okay, that makes sense. So, statal, show the Tyndall effect, can't be filtered normally, but can be centrifuged.
And just like solutions have solutes and solvents, colloids have the dispersed phase, which are the particles, like the fat in milk, and the dispersion medium, the substance they're spread throughout, like the watery part of milk.
And the source listed tons of examples based on the states of these phases, right?
Yeah, things like aerosols, which can be liquid droplets in gas, like fog or clouds, or solid particles in gas, like smoke. Then emulsions, like milk or mayonnaise, which are liquids dispersed in other liquids. And gels, like jelly or cheese, where a liquid is trapped in a solid network. It shows just how common colloids are in everyday life.
It really does. Fog, smoke, milk, jelly, all colloids. It's amazing how much complexity is hidden in plain sight. Okay, we've really dug into mixtures, solutions, suspensions, colloids. It's clear that pure is rarer than we think. But that brings us to the next big question. What is fundamentally pure matter made of, and how does it change? This takes us into physical versus chemical changes, and finally, the true pure substances, elements and compounds.
Yeah, distinguishing between physical and chemical changes is really fundamental to understanding what matter is and how it behaves.
So what's the difference? Let's start with physical changes.
Okay, physical changes are transformations that alter the form or appearance of a substance, but not its underlying chemical identity. Think about properties you can observe or measure: color, hardness, density, melting point, boiling point. A physical change might alter these, but the substance itself remains the same chemically.
Like ice melting, it goes from solid to liquid, changes density, looks different, but it's still H2O, right? Same chemical makeup.
Exactly. Water boiling a steam is another one, still H2O. Melting butter, chopping wood, dissolving sugar in water. These are all physical changes. The substance's chemical formula doesn't change.
Okay, so form changes, but identity doesn't. What about chemical changes then?
Chemical changes or chemical reactions are fundamentally different. Here, the substance does undergo a change in its chemical composition. New substances are formed with entirely new chemical properties. Bonds are broken and new bonds are formed.
Ah, so something genuinely new is created, like burning wood.
Perfect example. Burning wood involves combustion, a chemical reaction with oxygen. The wood transforms into ash, carbon dioxide, water vapor. Completely different substances with different properties than the original wood. Rusting iron is another chemical change. Iron reacts with oxygen to form iron oxide, or rust.
Cooking food involves a lot of chemical changes too, I guess.
Absolutely. Baking a cake, frying an egg. Those involve complex chemical reactions that change the ingredients into something new. The source even mentions burning a candle as having both physical change, the wax melting, and chemical change, the wax actually burning and reacting with oxygen.
That's neat. Melted wax is still wax, physical, but burning wax becomes CO2 and water chemical.
Precisely. And the source gives a great experimental example with iron and sulfur.
Right, activity 2.4. If you just mix iron filings and sulfur powder.
That's just a physical change. It's a mixture. The iron is still magnetic. You can pull it out with a magnet. The sulfur is still yellow. They haven't chemically reacted. They've kept their original properties.
But if you heat that mixture strongly...
Now you're providing energy to trigger a chemical change.
Hmm.
The iron and sulfur react to form a new substance, iron sulfide.
And this iron sulfide is totally different.
Completely. Iron sulfide isn't magnetic like the original iron. And if you add acid to it, it produces hydrogen sulfide gas, smells like rotten eggs, whereas adding acid to the original iron would just produce hydrogen gas. The properties are totally transformed, proving a new substance was made. It's no longer a mixture, it's a compound.
That's a really clear illustration. New substance, new properties equal chemical change. This leads us perfectly into the actual types of pure substances, elements and compounds.
Exactly. These are the bedrock categories of scientifically pure matter.
And there's some history here. Robert Boyle first used the term element way back in the 17th century.
1661. But it was Antoine Lavoisier, often called the father of modern chemistry, who later provided the first really useful experimental definition.
What was his definition, essentially?
Lavoisier defined an element as a basic form of matter that cannot be broken down into simpler substances by chemical reactions. Elements are the fundamental building blocks. You can't simplify them chemically.
Okay, the simplest chemical units. And we grew some, right? Metals, nonmetals.
Yes. The main categories are metals, nonmetals, and metalloids.
Let's quickly run through those. Metals.
Metals are typically shiny, we say lustrous, often silvery or golden. They're great conductors of heat and electricity. They're ductile, you can draw them into wires. Malleable, you can hammer them into sheets. And sonorous, they make a ringing sound when hit. Think gold, silver, copper, iron.
Common examples. And wasn't there a fun fact about mercury?
Yes. Mercury is unique. It's the only metal that's a liquid at standard room temperature. All others are solid.
Cool. Okay, then nonmetals.
Pretty much the opposite in many ways. They come in various colors. They're poor conductors of heat and electricity. Generally not shiny, not malleable or ductile, not sonorous. Examples include things like hydrogen, oxygen, carbon, like in coal, iodine, sulfur.
And there's a liquid nonmetal, too.
Yes, bromine is the only nonmetal that's liquid at room temperature.
Interesting parallel with mercury. And the third group.
Metalloids. These are kind of in between. They have properties that are intermediate between those of metals and nonmetals. Silicon is a famous one, used in computer chips. Boron and germanium are others.
So elements are these basic, unbreakable building blocks. How many are there?
We know of over 100 elements now, though only about 92 occur naturally. The rest are man-made, usually in labs.
Okay, so elements are one type of pure substance. What's the other?
Compounds. A compound is formed when two or more different elements combine chemically. And here's the key. They combine in a fixed proportion.
That fixed proportion seems really important. How does that make a compound different from just a mixture of elements?
It's the absolute crucial difference. A mixture, remember, has variable composition, and the components keep their properties. But in a compound, the elements react to form an entirely new substance with properties completely different from the original elements.
Like your water example earlier, hydrogen and oxygen are flammable gases.
Exactly. But combine them chemically in a fixed 2-to-1 ratio, HO. And you get water liquid, stable, extinguishes fire. Totally different properties. The composition of water is always HO. It's fixed. That defines it as a compound.
And you can't just physically separate the hydrogen and oxygen in water, right? Like you could separate salt and water by evaporation.
No way. Because chemical bonds were formed, you need a chemical reaction or an electrochemical one like electrolysis to break water back down into hydrogen and oxygen. Physical methods won't work on compounds.
Okay, let's summarize that difference then. Mixtures versus compounds.
Right, so mixtures. Elements or compounds just mix physically. No new substance is formed. The composition can vary. The mixture shows the properties of its components, and you can separate them by physical methods.
Got it. And compounds.
Elements react chemically to form a new substance. The composition is always fixed by mass. The new compound has totally different properties from the elements that made it, and you can only separate the constituent elements using chemical or electrochemical reactions.
That's a really clear distinction. Fixed composition and new properties are the hallmarks of a compound. Wow, what a journey. We started just thinking about pure milk, and now we've explored the scientific meaning of purity. dived into the different kinds of mixtures.
Solutions, suspensions, colloids.
Right, and saw how they differ. Then we looked at physical versus chemical changes and finally landed on the true, pure substances, elements and compounds, the fundamental building blocks.
It really gives you a new framework for looking at, well, everything around you.
It absolutely does. So here's something to think about as you go about your day. Next time you look at anything, the air, your coffee, a ring, the food on your plate, just pause for a second. Ask yourself, is this likely a pure element, a specific compound? Or, more probably, is it some kind of mixture?
And if it is a mixture, can you guess if it's homogeneous, like salt water, or heterogeneous, like salad dressing?
Yeah. Or can you maybe even spot the Tyndall effect, that beam of light cutting through a dusty room or foggy morning? It's seeing the world through this scientific lens. It reveals a hidden layer of complexity and wonder in the everyday.
What surprising new insights will you uncover now?